Welcome to the webinar today. As Mike said, I'm Zach Murphy from Velo3D, and I'm here with Andrew Carter from Stratasys Direct Manufacturing. Today we'll be talking about some complex applications in manufacturing for the energy industry and how state-of-the-art metal 3D printing can play a role in the manufacturing of these components. If you're at all familiar with Velo3D, one of the things that you'll know is that our main focus is on mission-critical applications. We're trying to solve some of the more challenging problems that you can find whenever it comes to specific geometries and the applications where those parts play a role. And one of the things that's common with these specific parts is that they tend to be highly optimized. And the optimization means that geometrically, they can be very complex. They also play a very important role within the larger system because often these are the parts that determine the global performance of these systems. So it's very important to get the parts right. And the manufacturing of these complex parts can truly be a pretty intense workflow. And what you run into with these parts often is that you have to compromise somewhere. So in manufacturing, if something's very, very highly optimized for performance in terms of the geometry itself, it can become very tricky to manufacture. And we see this as a trade-off between some of these 5 bullets that you see listed on the screen. So if it's a very high performance part where you need very high quality, the cost is often very high. And particularly if you're looking at applications that are kind of bespoke, something that you find in a lot of energy applications or like petrochemical pumping type of applications, you have very low volumes of parts. So you may have 1 or 2 of a specific, in this case, impeller design. And because there's such a low volume, the availability of these parts is pretty low. And again, this comes with added cost when you try to get these parts. So one of the things that Velo's really focused on is making sure that we can make these very complex parts successfully. And having customers like Stratasys Direct, who are kind of more capable of the complete workflow of delivering a turnkey part, is really a critical factor for us as a company to provide value to the end customer. As Mike referenced in the introduction, one of the questions that people often have is around the transition from more of a traditional manufacturing to what we call our digital industrial manufacturing. And with traditional manufacturing, what you often see with many of these parts is that making the final geometry requires multiple steps. So as you can see on this picture, which is kind of a turbine vane section, you have multiple machining steps. You have the inner hub and the airfoils themselves. You have the outer hub. There's a welding process that you have to go through to join the two pieces together, an inspection of the weld, final machining, heat treatment. It's a very complicated process even to get just the part itself before you go through all of the final inspection. And with additive manufacturing, one of the things that we see is that you can dramatically simplify getting the initial part at the very least. And I'm going to let Andrew talk to this a little bit more because he's going to go through the entire workflow for the impeller that we're talking about today. But the advantages of using Metal AM, and specifically Velo Metal AM, is that you can iterate much more quickly, you can refine the design, increase the performance, and really optimize the part for the function in which it will be playing a role. The other note from the introduction from the survey was that supports are really a critical concern in metal additive manufacturing. And even if you're an end customer and you're working with a very good contract manufacturer like Stratasys Direct who can take care of a lot of the headache around the supports, you're still going to realize some of the impacts from supports in terms of the cost of the part, because this plays a significant role in the post-processing that's required for the part. It also, in some cases, can even be so bad that you'll get a no bid, right? If a part is very complicated and would require supports that are essentially impossible to remove, which is the case for many of these kind of power applications, then in most cases, it's just not economical to make. And Velo3D can really help to address this through the capabilities that we offer with our support-free manufacturing. A great example of the use of support-free manufacturing is in shrouded impellers. And this slide serves to illustrate a little bit of the difference between what you might get from a more conventionally supported metal AM shrouded impeller versus the capabilities of the Velo3D systems and of manufacturers such as Stratasys Direct. And I think to go into those capabilities in a little more detail, I wanted to highlight three kind of differences in terms of the geometries that we're capable of printing. So if you've been following Velo3D, last year you would have heard that we're capable of printing down to 10 degrees without support structures. We've been continuously improving our process, and I'm happy to report that at this point we can actually print lower than that. So we're all the way down to 0-degree overhangs in certain applications without supports. The impeller that you see here on the left is a good example of that, where the shroud on this impeller actually goes down to a fully horizontal exit at the OD of the impeller. This also allows us to print some much larger inner diameters without support structures. So in the middle, we have a manifold, a proxy for a manifold. This is printed with about a 40mm inner diameter, but we're actually able to push that up much higher now. So we can go to essentially a 100mm or a 4-inch inner diameter on a horizontal tube and print that successfully without support structures internally. And another main difference of our system is around how it actually recoats the powder. And we do that in a way that doesn't apply any force to the powder bed, which allows us to print some very high aspect ratios. So we can print down to 10,000ths of thickness walls and print those essentially 16 inches tall. So you can get some extremely high aspect ratios, which is very useful for applications such as heat exchangers, which is really another critical application for power generation components. So with this overview of Velo3D's technology, I'd like to turn it over to Andrew to talk a little bit more specifically about the application that we're looking at today.
Excellent. Thanks, Zach. It's a pleasure to be here. And that was a great description of some of the state-of-the-art 3D printing features found on the Sapphire system that are really allowing Stratasys Direct to take on increasingly complex components that are designed for even more demanding applications. We're going to shift gears here a little, moving away from the additive system itself, and I'd like to direct our focus to the parts and applications additive is being leveraged to produce. I'd really like to think about how the industry is leveraging additive and the perception that industry has of additive. And in so doing, I'd like to suggest a new, or at least amended definition of part complexity to the additive community. But before I can do that, I need to provide a little bit of background of Stratasys Direct Manufacturing to really set the foundation of this perspective. So Stratasys Direct Manufacturing is an additive manufacturing service bureau or contract manufacturer. It's a company that is wholly owned by Stratasys as one of its subsidiaries. However, contrary to popular belief, we don't solely have FDM and polyjet systems. Rather, we have essentially all commercially available additive technologies. And at Stratasys Direct, we implement processes and controls around those technologies or systems to offer them as services to industry. We're comprised of 7 manufacturing sites spread across the United States and have over 3 decades of additive experience. Over those 30 years, we've produced more than 20 million components in over 150 different materials. And on the onset of any opportunity, Stratasys Direct provides guidance towards the best technology and process for the component and the end intended application. Within Stratasys Direct's technology portfolio is, of course, laser-based metal powder bed fusion, and that's the technology of interest today. Our additive metals fleet is composed of 18 laser-based metal powder bed fusion systems. They process 9 core alloys with a couple ancillary specialty alloys specific for various customers. The fleet is split between 2 facilities with similar additive capacity and redundant capability. By capability, I mean Stratasys Direct has added floor space dedicated to conventional tools to complement their additive systems. Now, these CNC centers are dedicated to the additive process, meaning if they're not machining additive components, they're machining jigs and fixtures to machine additive components. And in addition to that, we have the necessary inspection equipment in dedicated labs to look at dimensional stability via calipers, height gauges, ferro scans, as well as CMM inspection, as well as looking at cut up, metallographically prepped and polished samples of the deposited material. Now, most recently, last year, Stratasys Direct acquired the Velo Sapphire system, and the features described by Zach have opened Stratasys Direct to new applications and a wider range of part geometries, and ultimately a higher level of complexity. And this is a good transition to propose that alternative perspective of part complexity, or at the very least, what part complexity looks like now to the contract manufacturer. As the additive manufacturing systems like Velo, Sapphire machines are widening the geometries able to produce. And it's not necessarily geometric complexity that I'm talking about. Don't get me wrong, Velo is able to produce more complex components than any other systems out on the market, but their support-free process really makes that step essentially easy. The complexity comes with the requirements, not only necessary for the component to function, but also give the customers the confidence that the part will function as designed. And as this drawing suggests, these requirements far exceed simple dimensional requirements. In fact, this is a relatively simple part, but the argument is that it's made complex by all the requirements. And this is really shifting the focus of the conversation between the contract manufacturer, the additive contract manufacturer, with their customer. And it's shifting it away from the additive portion of additive manufacturing and really diving into the manufacturing portion of additive manufacturing. And this may initially feel like a settling remark. Customers in industry are coming from rapid prototyping where the part is essentially ready in days. And this has really skewed the perception of how to realistically implement additive manufacturing, regardless of whether this is for new product development or serial production. And to convey this point, I'd like to speak of 4 different scenarios or essentially steps that a service bureau must carry out and communicate with the customer to understand the true scope of an additive manufacturing project. The first step starts with negotiations, and I'm not talking about price. Instead, I'm talking about the requirements. A lot of these requirements require steps that aren't part of the core additive service bureau and require a level of understanding and experience that potentially may have not been explored. So discussions with the customer needs to dissect those requirements to figure out what is actually necessary and required to achieve or exceed, what requirements we might be able to simply report, and what other requirements might actually be best effort. Well, as we get to these more complex applications, we find out that the customers are really putting those requirements in for good reason and making the contract manufacturer essentially take all risk because those requirements are there to reduce the risk of the component failing in the customer application. So with the requirements understood and the complexity of those requirements understood, it's time to make a manufacturing plan. And that manufacturing plan is essentially an outline, a list of operations necessary to communicate what needs to happen to this part along the manufacturing path to deliver the component as the customer desires. And in the example that we were previously looking at with those requirements, we took those 10 basic requirements and it required Stratasys Direct to distill that into 35 different operations requiring 4 different work cells within Stratasys Direct and 6 different vendors. And we can quickly see here, this is starting to become very logistically complex. So after the manufacturing timeline is in place, or manufacturing plan is in place, we have to talk about timeline. And this has to be clearly communicated to the customer. Additive is accessed by customers because they believe that they can get a component quick. And that quickness is really relative, but it is still skewed because they hear a notion of a 5-day print is the elapsed time to deliver the component. So customers, even after imposing some of those more stringent requirements, are questioning us as a contract manufacturer, why wouldn't that part ship on the afternoon of the 5th day since it was a 5-day build? So we convey this notion of post-operations that at first glance might double the manufacturing timeline, because it's still additive manufacturing, of course. How could the post-operations being secondary to the additive process exceed the timeline of additive manufacturing? Well, when we dissect it even further, we can say that AM is followed by secondary operations as well as inspection. And post-operations somehow makes those operations less important. So I prefer the word secondary operations because they're just as critical in delivering a functional component in the end. Now we can see the typical timeline here is in 12 days, and I'm going to argue that is still even skewed with these complex geometries. Because when we turn back to the example we've been reviewing, we see the timeline here. And these are the necessary steps at a course level that the component and product needs to flow through in order for us to deliver the end use component. You can see AM all the way on the left there and the initial prescribed 5 days, and all the follow-on operations to deliver that component on day 50. And you even see QC instituted at more than one time, not necessarily all the way at the end. And that's actually a good thing. You don't want to be continuing to invest in component that you could have identified as non-conforming earlier. So what I'd like to do to kind of drive this point home is put these timelines all on the same scale. And what we see is the perception of AM all the way at the top and the reality at the bottom. Now, additive manufacturing, yes, is quick to get the near net shaped part, but to deliver that end use part, it requires multiple vendors as well as multiple secondary operations managed by the contract manufacturer. It's important to note at this point, a lot of those vendor applications, of course, require the component to be shipped, sometimes across country. So in the best case, the majority of the manufacturing time of these components is largely just sitting on the base of a truck in transit. So one last little notion of complexity that comes with these demanding components is the monetary investment that the contract manufacturer must stomach before they deliver the component. In this example, we're not solely talking about the time and material that the machine uses to build the components or the CNC centers and tooling costs there, but POs are cut by the contract manufacturer to vendors, increasing the overall initial investment of the component before it can be delivered. And one thing to note is that as additive stands, the most expensive portion is largely the additive deposition, and that's largely due to the machine costs. Contract manufacturers need to start this manufacturing plan with the most money down, understanding that there's risk with each follow-on step and each transfer to a vendor. There's a lot of risk that is taken on by the contract manufacturer right up front. And that's just part of the additive manufacturing process as it stands now. But now that we understand the timeline, the customer sees the list of operations, we can finally execute the job. And the manufacturing sequence gets sent to the shop floor, the build is kicked off, the parts get machined, mechanical properties are verified, and part requirements are tested and reported. And I hope we all now understand that it's much easier said than done, and brushing over all these secondary and inspection requirements is really doing AM a slight disservice. Now, why do we go through all of this effort? Well, it really boils down to there was no other way to economically produce these complex components, and there's no faster way to produce these components. And to demonstrate this, I'd like to look at an actual project where Stratasys Direct actually partnered with Hanwha Power Systems to produce a radial shrouded impeller wheel for use in a full-scale elevated temperature test. So to start off, we looked at the comparison between the current art of the additive manufacturing systems and compared it to the state of the art. So on top, we have support structures in red. On bottom, we have support structures in blue. And what we see is that Velo allowed us to greatly reduce the volume of material and surface area that the component needed or the system needed to support. And this really allowed us to deposit this structure. If we had to use the current art, build time would be too long, and it would have put support structures in areas that would be inaccessible to our secondary operations to remove. So straight off the machine, we have a near net shape part that met our overall size requirements as well as the geometric complexity requirements without adding all of that build time. However, the dimensional tolerances and the historical confidence in the process is not there. And that's where really Stratasys Direct's specialty and project management stepped in. So it was the combination of the state-of-the-art 3D printing and the project management that really has made the impossible possible, where the near net shape part becomes a functional component is all the secondary operations that wouldn't have even been allowed to have been executed if it wasn't for the system. Now you can see on this component that the vast majority of the surfaces have been improved in some fashion all during those secondary operations. But the process and the state-of-the-art 3D printer produces more than just a component that the customer is happy with. And it's also knowledge of the additive material process and confidence that it is ready for taking on these critical applications. So this effort with Hanwha Power Systems generated a wealth of data. Here we're looking at tensile properties as a function of temperature and comparing those to ROT Inconel 718 to MMPDS spec minimum values. At each point, we're comparing horizontal and vertical oriented coupons. In dark blue, we have the horizontal coupons. In light blue, we have our horizontal coupons. And the hollow data points are the yield stress, and the solid points are the ultimate. Buried in there is actually a comparison to legacy data generated by Stratasys Direct at room temperature and 1,000 degrees F. And what we're seeing is great overlay, not only in orientation, but also between data sets, really giving us confidence that not only are mechanical properties able to be achieved as expected, but we're able to do this on a repeatable basis. But when I present tensile properties to customers, even as a function of temperature, the next question is obvious. Is always, well, do you have any fatigue properties? Well, in these critical applications, especially rotating components that see thermal cycles, is fatigue. So Hanwha and Stratasys Direct put together a plan to test the fatigue life at 2 different ratios of the deposited material. And we took that data and compared it to the MMPDS anticipated ROT values. So on the top, we have the stress ratio of -1 and the dashed lines. On the bottom in the solid lines, we have a stress ratio of 0.1. And in the orange, we have our horizontal oriented coupons, and in light blue, we have our vertical coupons. The real takeaway here is that there's great alignment between the 2 different orientations of the fatigue properties. However, there is a slight decrease in the fatigue life for the additive material. But I'd really like us to, in the future, compare the spread of the data that is presented in the MMPDS handbook, and then share that these ranges are actually fairly well overlapping. Let me put it in a different way. There's a lot of noise in fatigue data, and the curves here that are represented are of highly variation of data. So all in all, the behavior is very similar to ROT properties, although slightly lower. And the end result, enabled really by the state-of-the-art 3D printer and then the project management of Stratasys Direct, is a component the customer is happy with dimensionally and material strength and integrity, and ultimately ready for use in their end application. So the message here is that regardless of whether or not it is a new product development, as this slide suggests, or repeat serial production, Stratasys Direct is here to leverage the Velo3D Sapphire platform to bring your application to its turnkey solution. I'd just like to say thank you for everyone's time. I hope this was informative, and please feel free to follow up with any additional questions.
Same here. Thanks to everybody for attending.
All right, great job, guys. And stay tuned for the next session. We'll be in touch.